Respected sir, this is Sirichandra from CSC to roll number 24951A05BN. Today I am going to talk about Cayley-Hamilton theorem and applications in n-partition matrices. Introduction to Cayley-Hamilton theorem. The Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic polynomial. This theorem has profound implications in various fields, including control theory and differential equations. This presentation explores its applications in n-partition matrices. Understanding characteristic polynomials. The characteristic polynomial of a matrix is derived from its determinant. It provides crucial information about the matrix, including its eigenvalues. Understanding its concept is fundamental to grasping the Cayley-Hamilton theorem and its applications in matrix theory. Let's talk more about Cayley-Hamilton theorem. The Cayley-Hamilton theorem is a fundamental result in linear algebra that states that every square matrix satisfies its own characteristic equation. This means that when you substitute the matrix A into its own characteristic polynomial, the result is a zero matrix. In similar terms, the matrix A satisfies the equation derived from its own eigenvalues. Steps to apply the Cayley-Hamilton theorem. First, compute the characteristic polynomial of the matrix A, which is P A of lambda is equals to det of A minus lambda I. Substitute the matrix into the polynomial. Replace lambda in the characteristic polynomial with the matrix A itself, resulting in P A of A. Verify the result. The matrix should be zero matrix as per the Cayley-Hamilton theorem. Next, applications of the Cayley-Hamilton theorem. Finding matrix powers. The theorem allows us to express higher powers of a matrix in terms of lower powers, which can simplify calculations, especially for large matrices. Solving matrix equations. It can be used to solve equations and involving matrices such as An is equal to lambda A of n minus 1 plus mu A of n minus 2 and continue by using characteristic polynomial. Control theory. In control theory, the Cayley-Hamilton theorem is useful in system analysis, especially in deriving state space representations of dynamic systems. Eigenvalues and eigenvectors. The theorem links the eigenvalues of a matrix to its characteristic polynomial, providing an alternative way to compute eigenvalues. The conclusion of the Cayley-Hamilton theorem is a powerful result in a linear algebra that tells us that every square matrix satisfies its own characteristic polynomial. It is a useful tool for simplifying matrix computations and is widely applicable in fields like control theory, system analysis, and matrix theory. Next is matrix partitioning explained. So this involves dividing a matrix into smaller submatrices. This technique is essential for simplifying complex problems and is widely used in numerical analysis and computational mathematics. Understanding partition matrices is vital for applying the Cayley-Hamilton theorem effectively. Application in control theory. In control theory, the Cayley-Hamilton theorem is utilized to analyze system stability and design controllers by applying the theorem to partition matrices. Engineers can simplify complex systems and ensure desired performance characteristics. Application in differential equations. The Cayley-Hamilton theorem assists in solving linear differential equations. By expressing matrices in terms of the characteristic polynomials, one can derive solutions more efficiently, particularly for systems represented in partition matrices. Let's talk more about application of Cayley-Hamilton theorem in differential equations. The Cayley-Hamilton theorem has important applications in solving differential equations involving matrices, particularly in systems of linear differential equations. By using the theorem, we can simplify the process of finding solutions to these systems, especially when the system is described by a matrix differential equation. Application of Cayley-Hamilton theorem in differential equations. Solving systems of linear differential equations. The Cayley-Hamilton theorem can be used to solve linear differential systems of the form dy by dt is equals to ay of t, where a is an n into n constant matrix and y of t is a vector function. The solution to such a system involves finding the matrix exponential e power at, which can be complex to compute directly, especially for larger matrices. However, by applying the Cayley-Hamilton theorem, we can express higher powers of the matrix A in terms of lower powers, which simplifies the calculation of the matrix exponential. This helps to avoid directly computing a power n and instead uses a characteristic polynomial to reduce the order of computation. Reducing higher powers to matrices. For a matrix A in a linear system of differential equation, the Cayley-Hamilton theorem provides a way to reduce the powers of the matrix in a system of equations. Since A satisfies its characteristic equation, we can replace higher powers of A by expressions involving lower powers of A. This simplifies the solution of the system. Matrix exponentials in solving non-homogeneous differential equation. In many real-world problems, we encounter non-homogeneous systems of linear differential equations of the form dy by dt is equals to ay of t plus f of t, where f of t is a forcing term. The solution to this system involves finding the matrix exponential e power at and solving the non-homogeneous equation using methods like variation of parameters or Laplace transforms. Finding general solutions. In some cases, the Cayley-Hamilton theorem finds general solutions to systems of linear differential equations with constant coefficients. Once we know the form of the matrix exponential, we can apply the theorem to simplify and express a solution without needing to compute cumbersome and matrix powers. And then, conclusion of the Cayley-Hamilton theorem is a powerful tool in the analysis and solution of matrix differential equation, particularly for linear systems of differential equations. It simplifies the computation of matrix exponentials, reduces the need for higher powers of matrices, and allows for efficient computation of solutions, especially in systems involving constant coefficient matrices. Next is computational efficiency. Utilizing the Cayley-Hamilton theorem with n-partition matrices enhances computational efficiency. It reduces the complexity of matrix operations, making it easier to perform calculations in large-scale problems often encountered in engineering and physics. Next is case study about robotics. In robotics, the Cayley-Hamilton theorem is applied to model and control robotic systems. By partitioning matrices representing robot dynamics, engineers can design more effective control strategies, improving performance and responsiveness. Next is case study and network theory. In network theory, partition matrices help analyze connectivity and flow. The Cayley-Hamilton theorem provides tools for understanding how networks behave under various conditions, leading to more efficient designs in telecommunications and transportations. Next is challenges in application. While the Cayley-Hamilton theory is powerful, challenges remain in applying it to complex systems. Issues such as numerical stability and computational overhead can arise when dealing with large partition matrices, requiring careful consideration. Future research directions. Future research on the Cayley-Hamilton theorem may explore new applications in emerging fields such as quantum computing and machine learning. Investigating its potential in these areas could lead to groundbreaking advancements in technology and mathematics. Summary of all the key points is that the Cayley-Hamilton theorem is a cornerstone of the matrix theory with diverse applications. Its utility in control theory, differential equations, and computational efficiency highlights its importance. Understanding its implications in n-partition matrices opens new avenues for research and application. The conclusion is that the Cayley-Hamilton theorem offers significant insights and applications in various fields. Through its relationship with n-partition matrices. Continued exploration of this theorem will enhance our understanding of complex systems and their behaviors. Thank you.